Dalton's atomic model 1803. John Dalton proposed that all matter is made up of atoms, which are indivisible and indestructible particles. He suggested that atoms of different elements have different masses and that they combine in fixed ratios to form compounds. Dalton's atomic model was based on his observations of chemical reactions and the law of multiple proportions. Experimental verification. Dalton's atomic model was verified through experiments such as the law of definite proportions, which showed that the elements in a compound always combine in fixed ratios, and the law of multiple proportions, which showed that when two elements form more than one compound, the ratios of their masses are always in whole number ratios. Applications. Dalton's atomic model provided a framework for understanding the composition of matter and laid the foundation for modern chemistry. It is still used today in the study of stoichiometry, which deals with the quantitative relationships between elements and compounds. Thomson's plum pudding model 1897. J. Thomson proposed that atoms were made up of negatively charged electrons embedded in a positively charged pudding of protons. This model was based on his experiments with cathode rays, which showed that electrons were negatively charged particles. Experimental verification. Thomson's plum pudding model was verified through experiments such as the cathode ray tube experiment, which showed that cathode rays were made up of negatively charged particles, electrons. Applications. Thomson's plum pudding model contributed to our understanding of the nature of subatomic particles and paved the way for the discovery of the nucleus. Rutherford's nuclear model 1911. Ernest Rutherford proposed that atoms had a tiny, positively charged nucleus at the center, surrounded by negatively charged electrons. This model was based on his experiments with alpha particles, which showed that some of them were deflected by the nucleus of the atom. Experimental verification. Rutherford's nuclear model was verified through experiments such as the gold foil experiment, which showed that alpha particles were deflected by the positively charged nucleus of the atom. Applications. Rutherford's nuclear model helped to explain why some elements were more radioactive than others, and paved the way for the discovery of isotopes. Bohr's atomic model 1913. Niels Bohr proposed that atoms had a tiny, dense nucleus made up of protons and neutrons, surrounded by electrons that move in circular orbits at specific energy levels. This model was an improvement over Rutherford's model and explained why electrons did not spiral into the nucleus. Experimental verification. Bohr's atomic model was experimentally verified by the spectroscopic study of the hydrogen atom, which showed that electrons occupy discrete energy levels. Applications. Bohr's atomic model helped to explain the spectral lines of hydrogen and paved the way for the development of quantum mechanics. Quantum mechanical model 1925. The quantum mechanical model describes the atom as a tiny, dense nucleus made up of protons and neutrons, surrounded by a cloud of electrons that move in three-dimensional space. The electrons in the atom do not have defined orbits, but rather occupy regions of space known as orbitals. Experimental verification. The quantum mechanical model has been experimentally verified by numerous experiments, such as the double-slit experiment, which showed that particles can behave like waves, and the photoelectric effect, which showed that electrons can absorb and release energy in discrete units known as photons. Applications. The quantum mechanical model has many practical applications in daily life, such as in the design of transistors and other electronic devices. It is also used in chemistry to understand the behavior of molecules and chemical reactions. For example, the quantum mechanical model is used in computational chemistry to simulate the behavior of molecules and predict their properties.